My name is Daryl Saraspe. I'm an engineer here at MIDAS. I'll be giving today's presentation. So as you know, today I'll be introducing a brand new geotechnical software program, GTS NX. And as you probably know, GTS NX is our new generation geotech software program. And today what I'll do is just talk you through some of the major features that are incorporated with it, as well as provide just an introduction to our company, as well as an overview of POW Foundation design. Okay, but before I go in detail about our main topics today, I just want to introduce the GoToWebinar features for those of you who are new to it. So just some main things I want to make sure of is that everyone can hear me clearly. Now, if at any point during the session you have a hard time hearing me, or you need me to adjust the audio, feel free to type into the chat box, and you'll be able to enter in any comments there. So the chat box is right over here, and once again, you can enter in any questions and click the send button. And I'll be checking the chat box periodically to see if you have any, if you need any issues, or if there are any issues with the audio. Now, if you have any questions throughout the course of the session, since we're sort of on a tight schedule here, I'd ask you just to reserve your questions for now, and then send them to my email address at the conclusion, and I'll get back to you in a timely fashion. Okay, so as we discussed, or as I said previously, this is the sort of the outline for the session. So first, I'll provide an introduction to our company, who we are, what we do. Next, I'll give an introduction or just an overview of POW Foundation design, certain things to take into account when doing POW analysis and design. And then I'll go into an introduction of the software. Okay, so at MIDAS, we are currently the world's leading engineering software provider. So we have branch offices throughout the world. Currently, I'm broadcasting from our United States branch office located in New York City. But as many of you know, since this is the Asian region, we have branch offices also located in China, Japan, and South Korea. And we're also branching out into Europe as well. So we're very happy to share our software with the world. We find that we provide a great service through providing engineers with powerful tools to help them optimize their designs and get results that are very competitive. Okay, and I just also want to introduce a couple of the projects that have been modeled with GTS, or not necessarily GTS, but with our programs in general. So the Burj Khalifa Tower, the foundation for this tower, as well as the structure itself, was designed with MIDAS programs. The Beijing National Stadium in China. The Sutong Bridge in China. The Rusky Island Bridge in Russia. The Shanghai Expo Pavilions building in China, and of course the Incheon Bridge in Korea. So these are large-scale, very landmark structures, and they are all something they all have in common is that our MIDAS software programs were used in the design and analysis of them. And something we also like to pride ourselves in here at MIDAS is that we consider ourselves technical partners with our clients. So a key part of our services, in addition to our software, is our online training. So throughout the course of the year, we have multiple online training sessions, both online as well as live. So here are a couple of sort of pictures from our event in New York City, where we had a bridge seminar with various engineers from the area. And then we also have MIDAS sort of worldwide conferences and seminars taking place all over the world, in Italy, the UK, China, Japan, Spain, etc. So just keep an eye out for any of the events that we'll be hosting in your area. We'd love to have you attend and to see how our services could help you, better achieve your goals. Okay, and then another thing that we do as technical partners is that we make sure that our clients are provided for from the beginning to the end. So typically, when you're first introduced to our services, you learn about our programs, what we can do for you. You evaluate the program, and then you decide to purchase it if you feel that it's a tool that can be useful for you. But at that point, that's just the beginning of the relationship. From that point, we make sure to provide plenty of sort of online customized training so that you have the ability to become, adept at the program. Eventually, if you're providing training and technical support, you can become an expert at using the software. So you can definitely develop an enhanced set of skills that will allow you to, excel at your current position and to really achieve your goals as a professional. So once again, it's sort of an ongoing process. We provide these technical seminars and training so that you can further develop your skills. And then as you can see, we're there for you from the beginning to the end. So from the very beginning, when you still have your project drawing in AutoCAD, when you're modeling it, So finally, when you're doing the meshing and the analysis, we're there to support you every step of the way. as you continue to, I guess, face certain challenges, we'll be there to help you out. So just for those of you who are already our clients, I'm sure you already know that if at any time you need help with your project, you can feel free to contact us. Okay, so now I'll give an overview of pile foundation analysis and design. Okay, so when to use deep foundations. So as you may know, that deep foundations typically consist of a set of piles. And these piles, what they do is they transfer the loading from the structure down past sort of softer alluvial layers down to denser rock soil layers. So for example, if you're working in maybe a project site where the top alluvial layer is rather deep and rather loose and it's not safe to build a foundation there, pile foundations allow you to penetrate that alluvial layer and once again transfer the loads to more solid and more sort of steady, stiffer foundations. So also if you're dealing with large uplift forces, pile foundations or deep foundations are a good way to stabilize or to counteract that. And if you're dealing with any sort of collapsible or expansive soils, once again soils that form a very sort of depth or deep top layer that's unstable, pile foundations are good to sort of penetrate that and to get to the more stable soils. Also, if you're dealing with high lateral loading, pile foundations are much better at counteracting that or be stabilizing against that than shallow foundations just because they reach deeper into the soil. And also if you have any sort of tilting loads, so I know a lot of bridge abutments face tilting loads from various forces. So once again, any combination of forces in the lateral and vertical direction, pile foundations are especially good at resisting that. And then scour effects. So scour effects is something that's a very sort of limiting factor when it comes to bridge abutments and foundations. So what happens with scouring is that eventually over time this water flow will start to wear away at this foundation. But because pile foundations are so deep, even if the sort of top layer of this foundation or the soil is taken away, it can still be very stable despite the scouring effect. So once again, for a lot of bridges that are built over rivers or fast-moving water, where scour would be an issue, pile foundations are good at counteracting that because once again they reach very deep into the ground and they're more stable. Whereas with a shallow foundation, a scour effect would definitely over time compromise the stability of the structure and the foundation. And then any sort of stability risk. So once again, if you have maybe if you're doing an excavation nearby by a nearby adjacent structure, or if you're building your foundation against or near an excavation, pile foundations are especially good at stabilizing the structure against this sort of criteria. And then especially large or heavy loads. So this is an example of a pile raft foundation. So because high-rise buildings and suspension bridges and other sort of large high-end structures have such great loads, pile raft foundations are really the only realistic way to support these structures. So we'll talk more about pile raft foundations in particular, but just keep in mind that when you have a very large load caused by, once again, skyscrapers, high-rise buildings, etc., then piles or deep foundations are the only realistic sort of foundation for those types of structures, just because they're so large. Okay, so an important thing to keep in mind when doing your pile design or your deep foundation design is the ultimate bearing capacity. So the ultimate bearing capacity consists of several factors. Ultimately, it's a combination of shaft resistance and tip resistance, as you can see here. So because of if you're driven pile here, you'll have a certain amount of resistance both from the skin friction of the shaft as well as the sort of from the foundation at the base or the tip of the pile. But also keep in mind that the Q sub S, or the shaft resistance, is a function, or it's dependent upon the type of soil that you're working with. So for example, if you're working in clay type soil, then it would be dependent upon C sub A, or the adhesion. Whereas if you're working in sandy soil, it'd be a function of F sub S, also known as the skin friction. So keep that in mind as well. And then also the tip resistance is a function of the area of the tip. So obviously the larger the area of your tip, the more resistance you'll be able to get. And also another thing to keep in mind is that based on the fundamental theory, other factors need to be taken into account. So as I said, soil type, but also installation method. So whether it's a driven or cast in place pile will affect your bearing capacity, as well as the type of material. So typically concrete is used for deep foundations, but there are certain cases where steel pipes are used as well. And obviously if you're using a steel pipe, that's going to affect the amount of skin friction on your pile surface. Okay, another thing to keep in mind is the settlement. So the total settlement is just the the summation of the elastic settlement. So the deformation of the pile once the load is applied to it. The tip settlement, so any sort of settlement that occurs at the base, when the soil compresses. And then also shaft settlement, so the interaction or the skin friction that's occurring between the skin or the face of the surface here and the soil itself. Okay, so another thing, as far as a deep foundation is concerned, there's a method called PY analysis that's typically used for smaller scale deep foundations, and essentially it's based partially on Brom's method. And as you can see, this B factor here, beta, it's a function of the coefficient of horizontal subgrade reaction, the diameter of the pile, and also the stiffness of the pile section. Now, as far as PY analysis is concerned, there's certain points to be noted. So first and foremost is that different PY curves have been developed for various soil types. So if you look to this picture here on the left, you'll see that this pile has been driven through 4 different soil layers. And each of these soil layers has a different PY curve. So that's an important thing to keep in mind, that for every sort of soil layer that your pile interacts with, you'll have to have a separate PY curve for each. So these PY curves, they reflect the nonlinear behavior of the soil. So as you can see, each of these curves is nonlinear. So they can more accurately describe soil behavior as the pressure is increased. And as far as the analysis summary, the pile is the divided beam, and the soil is modeled with nonlinear springs. So the PY curve is your input parameter. So if you're doing a non-finite element analysis, then you'll have to be aware of your PY curves and model them accordingly. So what these PY curves do is they calculate the deflection of each pile segment. So each of these segments, the PY curve will calculate your vertical and your horizontal deflection. And depending on the deflection, you can calculate the soil resistance from the PY curve. So obviously, certain soils resist resistance more than others. So these directly affect your deflection calculations. And deflections and soil pressures naturally are interconnected. So this is sort of the relationship that the PY curve represents. And then you need to redo your iterations to obtain the correct value. So typically, as far as software programs that are out there, they'll take care of the iterations for you. And they're based on the finite difference method. Okay, so now let's give a brief overview of the differences between PY analysis and numerical analysis. So, PY analysis, which you just went over, the soil behavior is based on the PY curve, whereas numerical analysis, it's based on the constitutive model. So typically we use the Moore-Coulomb model, and in certain cases we use the modified Moore-Coulomb model. I'll get more into that later during the demonstration. As far as pile elements, everything's modeled as a beam, but with numerical analysis you can model it as solid elements or as a beam element. So you can model both linear and nonlinear behavior. So depending on, I guess, their project scope, you may want to model it as a solid element, but we'll get more into these options in the next couple of slides. Modeling, it's in the PY analysis, is a beam plus a nonlinear spring, whereas numerical analysis, it's 2D or 3D structural models. So there's more versatility in that respect. As far as soil interaction, it's all based on the PY curve, which we just discussed. With numerical analysis, it's based on interface and embedded elements. So these particular elements are very specialized, and they're very sort of accurate when you're doing any sort of soil structure interaction, not only for piles, but for any sort of general geotechnical structure. And we'll get more into how these are particularly useful, once again, in the upcoming slides. The upper structure can be modeled partially. There's a program called FBPeer which allows this. Whereas with numerical analysis, you can fully model your upper structure. So if you want to maybe model a couple of basement levels, or maybe a certain, like a large raft foundation, or even just the entire structure itself, it's fully capable of that in finite element analysis. Adjacent structures can't be taken into account in PY analysis, whereas in finite element modeling or numerical analysis, that's not a restriction. You can model adjacent structures and adjacent excavations. Construction stages can't be modeled in PY analysis, whereas with finite element analysis, if you have a long construction stage sequence that you want to model, you do have that option. So once again, the main sort of thing, I guess, to take from this is that numerical analysis is more geared towards higher-end projects or projects with more variables, whereas with PIY analysis, these are more geared towards conventional, very simple, straightforward projects. As far as design applications, as I said, these are sort of geared towards conventional, smaller-scale projects, whereas numerical analysis is really more geared towards I guess higher level or projects that have much bigger scope. So it's a state-of-the-art analysis. And then as far as software that's available to you, Pile, FB Peer, and then SoilWorks, which is our 2D sort of conventional program for geotech work, all handle PY analysis. Whereas numerical analysis, GTS NX, FLAC, and Plaxis are sort of the main leaders in the industry when it comes to deep or numerical modeling of deep foundations. So as far as pile groups, as you can see, if you have a group of piles, there's a pile cap put into place here, and a lot of the design work goes into deciding the spacing of your piles as well as the size of the piles themselves. Now let's talk about pile raft foundation. So behavior of a pile raft foundation is very complex, and it's more complex than a single or group pile behaviors. So with pile raft foundations, you can do away with a PY curve approach, several iterations for a single pile. But for pile rafts, it's very important to use numerical analysis programs like GTS NX. 3D analysis is pretty much just necessary for these types of foundations. So here's why. Pile raft and their bearing behavior is a very good example for soil structure interaction. So if you look here on the left side, we have a raft separated from the pile. So the raft itself has its own two interactions with the soil around it, and the pile has interactions with the soil around it as well. And then there's an interaction between the pile, the raft, and the piles themselves, which is a little bit summarized here on the right side. So as you can see, these 4 arrows sort of showing the interaction. We have raft soil interaction, we have raft pile interaction, and we have pile to pile interaction. So these interactions are very critical in governing how the piled raft will behave and perform and its bearing capacity at the end. So the total bearing capacity of the piled raft will be the summation of the bearing capacity of the piles plus the bearing capacity of the piled raft. And the pile bearing capacity is in itself the summation of the base capacity plus the shaft capacity. The raft bearing capacity is at the contact stress over the area of the rafts. And this total bearing capacity combined by the raft should be larger than the applied loads multiplied by the factor of safety. So just keep in mind that, once again, these interaction influences really sort of make the analysis of pile raft foundations very complex. That's why numerical analysis is so important. Because it takes something that's very complex and it simplifies it to a degree that makes it much more accessible and much more sort of realistic to undertake. Okay, so now we'll go into the numerical analysis of pile foundations. So there are 3 main numerical analysis methods that I want to go over. So first is a solid to element model, also known as a solid to solid interface. The second is the beam to solid connectivity model. And then last is the line to solid interface model, also known as the embedded pile. So first let's discuss the solid to solid interface. So as you can see, this particular model consists of a model, this consists of a solid, which is modeled as a pile element meshed into a set of solids, as well as an interface, which are sort of modeled there along the surface. So the main thing to sort of take from this example, or to take from this analysis type, is that the solid element, the pile, is modeled as solid elements. So main things to pay attention to is that this model definition and mesh generation can be elaborated for a large number of piles. So just imagine if you have a large pile raft foundation with maybe a couple of dozen piles. As you can imagine, for those of you who are experienced with finite element analysis, the analysis would take a very long time, just because to mesh all of these piles would create a large set of data for the program to analyze. So for really large scale, very large pile raft foundations, this sort of modeling isn't really very realistic. The model ultimately would be a little more complex than it would need to be. Whereas if you have sort of a smaller pile group foundation, or even just like a single pile, then this would be more realistic, because even though you have a very high level or highly detailed model, as long as it's within a sort of smaller scope, it's very reasonable. It's still reasonable. So once again, all those extra elements can lead to very long computation times. And then also pile forces and moments are not directly available in post-processing. So an important thing to remember is that 3D solid elements, when you model with that, you can't get your moments and your shear forces and your axial diagrams. So if you want to get those diagrams or those sort of results, then you need to model these as beam elements, which we'll discuss later. And then once again, interface behavior as far as elastic, non-elastic, Coulomb friction, and user-defined behavior is modeled with these interface elements. All right, so now let's talk about the beam connectivity model. So as you can see here, now the model consists of your solids, your soils, which are naturally modeled as solids, but then you have your 1D beam element here. So as you can see, the pile element is idealized as a one-dimensional beam. So certain points of attention for beam to solid elements is that the nodal compatibility requirements, geometry modeling, and meshing of the soil elaboratives. So keep in mind that whenever you're creating a finite element model, it's really important to establish nodal connectivity. So one of the main issues of the beam to solid connectivity model here is that this beam will have a series of nodes, and each of these nodes needs to connect, or needs to have a connection here with the with your solid elements. So just imagine, though, maybe you have to go back and you have to change your model. That's something that could take a very long period of time, especially to establish that nodal connectivity. If you have a large number of piles and you need to make some changes or you need to do some remeshing, you might have to go in there and one by one establish nodal connectivity, which could take an exorbitant amount of time. So as I just said, for pile rafts with a large number of piles, this technique produces large models in a very long computation time, mainly because nodal connectivity needs to be established. And when you're doing a design, or you're on a project that's being designed or worked on for over a period of time, naturally there are going to be changes. So it's not really very realistic to use this type of model for a large scale pile raft foundation. So once again, for this type of model would work better for a small scale project, maybe a single or a group pile, similar to the other method I just showed you. Now let's go to our final method, our line to solid interface model. So as you can see, this model consists of, once again, your ground is modeled as solid elements, but then there's a very special sort of element here that allows you to model your piles without worrying about nodal connectivity. And it also contains these line to solid interface elements. So just to elaborate here, the pile and solid geometries and meshes can be specified independently. So this is very important. So you don't have to worry about establishing nodal connectivity between the solid elements of your soils and then the beam elements of your piles. So because of that, it makes it very easy to make project changes or to make sort of design changes, very quickly. So you don't have to go back and reestablish nodal connectivity. You can actually, you can delete your pile and then put it somewhere else, or you can shorten your pile, etc. And nodal connectivity will be established, or not necessarily nodal connectivity, but there's just connectivity between the elements themselves will be established for you. And then in order to account for soil structure interaction, these nonlinear friction slip properties called line to solid interface elements are there for you. So it's just a matter of, you have your solid elements for your soil, you have your pile elements for your piles, but then you also have a separate set of elements for your interface, or for your soil structure interaction that are defined using these elements here. And once we go to our final demonstration, I'll give you a quick sort of glimpse at how these are modeled. And so the main sort of advantage of this method is that it reduces computation time, especially for like a large pile raft foundation. This sort of model is ideal. Okay, so now let's move on into our introduction of GTS NX. Okay, so what I'll do now actually is I'll pull up a quick video which is available on our website, MIDASGTSNX.com. And for those of you who are still looking to the program, the website is an excellent source of information if you're looking for specific design specifications or specific features it has. This website has all the catalogs, and it has in-depth sort of technical specs. But what I'll do is I'll just play this video that gives a brief sort of introduction to sort of the overall sort of gist of the program and what it can do for you. Okay, so as we said, at MIDAS we're a worldwide company. Our project or our programs are used throughout the world for a lot of high-end projects or conventional projects as well. So as far as MIDAS, or as far as GTS NX is concerned, it's sort of an all-inclusive software program that can handle everything from, as you can see, seepage analysis. So a lot of large-scale dam projects and earth levees have been designed with the program. So any sort of rapid drawdown or seepage flow or flux that you want to analyze, you can model that with the program. Okay, and its capabilities, once again extend to bridge foundations or bridge abutments. So if you want to analyze, the effects of scouring, or once again, if you want to do any sort of coupled analysis that have to do with seepage or slope stability or the foundation, you can do that. Any sort of 3D modeling for your tunneling or large underground structures, various subway systems and tunnels have been modeled in 3D using GTS NX. Several sort of projects here in America that involve large-scale subway designs or subway systems. GTS NX was used heavily for those. And also, if you're doing any tunneling, a lot of tunnel engineers here in the East Coast especially use our software for their projects to do the construction stage sequencing and any sort of like 3D tunnel connections. It's used very commonly for those projects. Okay, and once again, here's some more examples of some tunneling projects that are possible with the program. So with tunneling, you do a lot of staged excavation, and that's very important. Oh, and also for bridge abutments. So as you can see, that's a very large-scale bridge pier. The pile foundations were designed with that. And also, pile foundations of large structures or high-rise buildings. The Burj Khalifa Tower is just one example. But many large-scale sort of high-rise buildings, or the foundations of those anyway, were designed with GTS NX. So those are just a couple of examples of the sort of project types that are available to you or that you can analyze with confidence with the program. Okay, so now going back to the presentation here. Just give a second here for the page to load. So yeah, now let's go into a little bit more detail about what you can do with the program. So as you can see, any sort of static analysis or nonlinear static analysis is typically, for excavations or shallow foundations. Any sort of construction stage sequencing, can be done with static analysis capabilities. Once again, construction stage analysis, consolidation analysis if you're doing immediate settlement, or consolidation for clay soils. The program handles that. And then stress steepage fully coupled analysis. So if you have, like, for example, a dam or a levee, and you want to do your seepage analysis in combination with your slope stability analysis, you can do that very simply. And then you can model multiple sort of transient stages or steady state stages for rapid drawdown or changes in water level. And then dynamic analysis if you're doing any sort of seismic analysis. For example, if you're doing maybe earthquake loading or dynamic loading. The program also handles moving load analysis. So if you're designing for the moving load of a train or cars, you can model that very efficiently with the program. And once again, slope stability analysis and SRM and SAM methods. So as you can see, the program is all-inclusive. So if you go with GTS NX, you'll essentially have a geotechnical program that can handle any sort of application for you. So instead of having sort of several different programs that each is very specialized, you can have one program that can handle everything for you on a very simple, easy-to-use platform. So that's one of the key advantages of the program, is that once you learn how to use GTS NX, you'll have the ability to branch out and to do all these other analysis types because the interface is seamless for each one. Okay, so this is just the basic sort of framework of the program, and I'll go into more detail later on, but essentially you have your work window where your model is done. You have your tree ribbon here where all of your commands are made. You have your work window that keeps track of all of the elements that you create. So you can, once your project gets sort of larger in scope, you can easily sort of filter through everything that you create. And then you also have various sort of task panes and table windows that allow you to view your data. So what I'll do is I'll play this quick video that gives a quick demonstration of what the program is sort of capable of, or it gives a quick demonstration of any of the modeling capabilities of the program. So as you can see, the language can be shifted from Korean to English, Japanese, several other languages. So whatever language you speak, you should be able to access a language anyway that's accessible to you. So as you can see, you can have multiple model files open in the same same program. So you don't have to open a separate model file. You can view them all separately, or you can view them all simultaneously as well. And this is an example. As you can see, you can go from each model and check the results. You can do the modeling, etc. So this really allows you to sort of multitask a lot easier. So now we're just going through the ribbon menu, and as you can see, it's very easy to go from your various steps. So for example, here are your geometry commands. If you want to create any sort of 3D geometry, and the instructions are available to you that sort of give you a preview of what each command does. So that's another useful feature. Okay, so now we're selecting some solids, and what you can do is, you can create the meshing very seamlessly. It comes with a very advanced mesher, so multiple mesh sets can be created simultaneously. So it's just a matter of selecting, your solids, selecting the mesh type you want to create, and now we're, assigning some loading. So as you can see, loading is very sort of seamless as well. You just select the surface that you want to apply your load onto and put on the magnitude. And then you can switch from one project to the other very simply. So you only need to have sort of one window of the project open, and you can view multiple files. Okay, so another great feature of the program is its ground modeling capabilities. So for example, if you're working in projects that are in 3D, a lot of the times you'll have these complex or these detailed contours. So for example, here's an example of a sort of a digital map in a DXF type. What you can do is you can import these maps into the program and import the coordinates to create these very detailed and very accurate contours with very sort of a limited amount of effort. Also, if you have like a number of boring hole data, what you can do is you can just import these directly into the program, enter the coordinates, the depths of the various soil strata, and the program will extrapolate the various depths of the contours for you in 3D. So what I'll do now is I'll play a quick video that shows this capability in action. Okay, so for example, if you have an AutoCAD or a DXF file, you can just import your coordinates, or you can import the drawing, excuse me. And then from this, let's say you have sort of several boring holes as shown here. What you can do is you can use a bedding plane option, and you can use this to define your plane. So here, the user's just entering the name of the bedding plane, and then he'll just select these several boring logs or the boring holes. He'll enter in his coordinates, as you can see here. So these are just the various depths of the soil strata. Okay, so he'll select that coordinate section, and he'll put in the various depths here in the distance. And if you see the preview here, as you can see, what the program has done is it's taken the various sort of boring logs, and it's used the information to create a set of detailed contours for each of the soil strata. And now that the soil strata has been defined, what you can also do is see if you have like a very detailed contour map available to you, you can open that, or you can import it, excuse me. And using this feature, the TGM feature, the Terrain Geometry Maker, you can take your various curves, as shown here, and you can use the this 3D AutoCAD file to create a 3D surface that you'll later use to cut a solid and to make a detailed 3D model. So as you can see, here's the surface. You just have to save it under a separate file. Okay. And as you can see, now you just have to import it into the program itself. So once you import it, as you can see, you just select your spacing. And now the next step would just be to create a sort of 3D or set of 3D soil stratas. And you can do so very simply just by creating a soil block. And then just using the advanced 3D solid features, you can just make several cuts along the length of that block, just using the surfaces that you've defined. Okay, and as you can see, your soil strata has been defined. So it's very simple and it's very straightforward. So this is something that would have taken hours to do with other older programs, but within just a couple of minutes, as long as you have all of your data ready, you can create a very detailed 3D model. And last, let's go over a couple of the sort of results options that are available to you in the program. So one of the great advantages of numerical modeling is that you can you have this wide array of sort of results available to you. One of the things, though, is that you need to have a tool that can extract those results. Just because you have so many, you want to find or to extract the results sort of importance to you. So GTS NX comes equipped with various sort of result extraction tools that make it very easy and very straightforward to find the results that you need and to display them in a way that's very convenient and that's very accessible for a client or a colleague to look at as well, so they know exactly sort of what's going on. So one of the key sort of results or the result extraction tools is the probe result function that allows you to tag any point along the model and get the exact result. Okay, so as you can see, we can switch from model to model. So here's like a sample tunneling model. And what you can do is you can also create what's called a clipping plane. Now I'll discuss this more in detail during our last demonstration. But you can take your 3D results and you can use this clipping plane to go along the length of your model to see the different, I guess, contours of various points along any axis. And then, as you can see, you can also create a time-based analysis so that you can see how these sort of change over time, or the results change over time. You can get your maximum and your minimum values, your critical values at a mouse click. So as you can see, it's very easy to sort of manipulate the display settings to show exactly what you want. And using those probe result options, you can also put those numerical values as well directly on the screen. Okay, so here's a sample, I guess, embankment or a seepage type project. So here's the ISO surface. So you can isolate a contour or a specific value layer that's important to you or that you want to see. And once again, that's something that I'll go into more detail in later on. And then also for seepage projects, flow paths are very important. You want to see what direction your water is flowing for various nodes. You just select your nodes by clicking directly on the screen. So as you can see, the contours correspond to various sort of magnitudes. And if you hit the play button, you can get a better visualization of how your water is sort of flowing from areas of high water pressure to areas of low water pressure. Okay, and once again, you can view multiple files simultaneously. So that's just a brief introduction to the program. And now what I'll do is I'll provide a live demo session for a 3D abutment foundation for this particular project. So this is a project that's available, on the website through the tutorial. So if you want to download this project later on, just go to our website and go to the tutorial section, and you'll be able to view it. So it's right here under tutorials. But as far as the project itself, as you can see, I have a finished version here. And before I go into the results section, I just want to provide a brief sort of introduction to what's going on with this project. So first, let's take a look at our material model. So if you go up here to geometry, to static slope analysis, this tab, we go to material. We have all of our material properties listed here. So as you can see, it's all based on the more Coulomb material property. If I go to modify, and under model type, as you can see, I have various constitutive models available to me. So the modified more Coulomb model is available to me for nonlinear analysis, modified Cam Clay for a settlement or consolidation, Duncan Chang, Hoek Brown for a rock type analysis, Drucker-Prager, etc. So there's no real limitation to this sort of analysis you can run. Okay, and an important thing to keep in mind is just the existence here of the different pile type elements. So as you can see, I have my regular pile element that, so I'm modeling my pile as a beam, and I just have its various sort of structural elements here. But then also I have an interface element in which I have my K sub n or K sub t values just to model the soil structure interaction of the piles. Actually, let me get you a better view of these piles here. As you can see, if I go to the left to the work window here, I have everything I created listed. So I have all my meshing done. Let's say I want to take a look at my pile elements. What I can do is I can turn the mesh sets off and isolate just my pile elements, and then zoom in here. So as you can see, here are my pile elements. So an important thing to remember, as I discussed previously, is that because you're doing a deep foundation analysis with these pile elements, you have certain mesh types or mesh sets that need to be assigned specifically for these elements. So first and foremost, your pile beam elements. So it's sort of hard to see, but as you can see, as I turn them on and off, you can see the color sort of change. So originally this was just a series of edges, but then I assigned this particular property to these edges, so now they have the pile element properties. Also, I have my interface element. So what I'll do is I'll turn it on and off, and as you can see, the color changes as well. So in addition to my pile element, I also have my interface element modeled on top of that. And then last, let me see if I can move the view over for you. So pay very close attention to this bottom layer here under pile tip. Actually, let me switch the view again. So just pay attention to this bottom area here. As you can see, I have my pile tip element or my pile tip properties assigned as well, so that I can account for my bearing capacity for the tip, as well as the any sort of displacement or axial strain that occurs at the tip. So if I go to my mesh sets here, or under property, as you can see, I have my pile tip element. So I have my tip bearing capacity and my tip spring stiffness. So just keep in mind that whenever you do your deep sort of pile foundation analysis, that you have to have, typically these three properties or these three mesh types at least defined, so that later, you'll be able to. As you can see, I have my section defined. So I think, yeah, this is just a pipe element, but if any sort of a structural element you want to create, whether it be a T section or an H section, etc., it's just a matter of entering your dimensions. So that's something that's really great about the program, is it provides a very user-friendly interface to create these larger scale or more complex models. Another thing I want to sort of bring attention to is what's called the gauging shell element. So what I have here is this base slab that's going to be concrete, but I also want to get a certain set of forces that are acting on top of this this element. So because these are 3D solid elements, you need to create a gauging plate element in order to get certain moments or certain stresses acting on this top layer here. So just using this gauging shell element, just using this gauging shell element, I have applied it to the top of that, so that way I can get a certain set of results there, and I'll show you that in the results section. So another thing I want to bring attention to here is that this analysis will be what's called a construction stage analysis. So in other words, what I want to do is I want to start off with just what my project looks like at the very beginning, and sort of go step by step from the excavation to the construction of the piles and the abutment to the addition of this embankment here. So if I go to static slope analysis and I go to stage set, as you can see I have two construction stages created. So for this particular project, what we wanted to do is we wanted to see the difference of putting in this foundation with and without piles. So first let's take a look at the first construction stage. Okay, I'll move this over for you. I'll make sure to set the show data option to activate, so that way I'll only show what's activated for each stage. So as you can see in our first construction stage, it's just the initial project site, so there's no construction, there's no excavation whatsoever. And also keep in mind that this particular mesh set, this block here, actually consists of a weathered soil material property, and then later on we'll change it to a concrete property. So here in our second construction stage, let me save the data here. So in our second construction stage under the excavation, as you can see, this top portion here has been removed. And if you go here under the deactivated section, as you can see, that base slab, that base mesh set has been deactivated. So just using these two windows here, we can tell the program what we want activated and deactivated in each section. So once again, if I go to the first section here, the first construction stage under foundation, all I have activated are my, my soil strata, as well as my self-weight, my boundary conditions. Now if I go to my third construction stage, under structural arrangement, as you can see now I have the abutment, now the base slab has been inserted. So as you can see, the base slab has been reactivated, but then also there's a specific boundary condition called structure, which essentially tells the program here that this base slab now consists of a concrete material property instead of a weathered soil property. Also notice that here I have my piles, but they're not activated for this construction stage. This is because this first construction stage, we just want to model the foundation without our piles. And then in our second construction stage, what we'll do, or excuse me, in our second construction stage case, what we'll do is we'll model these pile elements. And then the last couple of construction stages are very straightforward. We have our embankment, and then our last construction stage, we have our surface load. So we did add a sort of surface load to this top portion here. So now what I'll do is I'll just show you the second construction stage really quick. Okay, so it's fairly the same. The only difference is for this third construction stage under structural arrangement, as you can see, now we have our pile tip, our pile beam elements, and our pile-to-pile interface element activated. So now, this is construction stage set 2. We have two variations that we modeled, and we can directly compare and contrast these results in our final analysis. So now, what we'll do is let's take a look at our final results. Let's go to the results section. Oh, and yeah, before I continue, another thing I want to show real quick is just the geometry, and I'll show you just the loading here. So if you go to analysis, and we're going to go to sort of surface load. As you can see, I have a surface load applied, then I also have my self-weight. And then also, under that base slab, so another important thing to note is that change in construction or constraint, that change in element here. So under the boundary condition here, under structure, as you can see I have a change property option put on. So if I turn this on, as you can see I have it specified for this slab. And if I take a look at what I've created, as you can see I specified the property to change from whether it's soil to concrete. So this is particularly important when you do construction stage analysis, particularly for like pile mat foundations or any sort of large mat or raft foundations. Typically you'll have a mesh set that will change properties from soil to concrete. So using this option you can simulate that in your construction stages. Okay, so now let's go back, let's turn all of our meshing on, let's zoom out, and now let's go to our results. So we can go to pre-processing, or excuse me, post-processing here. As you can see, let's minimize these. I have two main sort of construction stage sequences. My first case without the piles, and if I go to my first sort of stage here and I go to total translation, so this is another way to find your settlement. So as you can see, nothing happens here. Everything is 0 just because this is just our initial site conditions. But if we go to our second stage here under displacements and we go to total settlement, as you can see this has been removed. And actually let's turn this deformation off for now. And as you can see, our deformation is occurring here at the center, and you can use this option here. You can use this legend to get a better idea of what these contours represent. So it's about 0.0015 meters of displacement. If you want to change your units from meters to say maybe centimeters, you can get a better view. So it's about 1.16 centimeters of maximum displacement here. And once again, you can use the probe option to get a series of sort of contours, excuse me, a series of values. Okay, so now let's take a look at sort of the clipping plane. Let's sort of take a cut here, and let's see what it looks like sort of cut down the center. So here, in order to do that, we just use this clipping plane to reverse it here. And as you can see, we can move along the length of whatever axis. So this axis is the y-axis, and we can see how the contours change as we move along it. So now, let's what we'll do is let's add 3 different planes here. Let's close this. And as you can see, you can create any number of slices that you need. So you can go along the length, you can use these slices to get a better idea of what's sort of going on or how the settlement is occurring along the length of the y-axis. Okay, so that's your cutting plane. And I'm sure you noticed that there weren't any piles in that particular, or in this case. So what we'll do is we'll take a look at the sample with the piles in just a second. I just wanted to show you here under displacement. So as you can see, now we have the introduction of our structural elements and structural properties here. So in addition to settlement, you can also have your your shell element forces, your solid strains, etc. They're all available to you. So now let's fast forward actually to our pile element. So if we open this up and go under structural arrangement, now for this particular case, as you can see, we have an extra option here called beam element forces. So now let's take a look at what's going on with our pile elements. So let's say we want to take a look at our axial forces, our shear forces, and our bending moments. So in order to view that, make sure to just deactivate everything except for your pile elements here. So if I go to results, and then I click on axial force, and then I zoom in here, as you can see, I can get my axial forces, I can get my shear forces, and then also I can get my bending moments. Okay, and I can get them for each of my stages. So for example, when the embankment's introduced, I can open up my beam element forces and I can see how it changes. So my bending moment when the embankment's introduced sort of shifts naturally, or excuse me, in the y direction. Let's check that. It sort of shifts, and you can see how that changes for each of your construction stages. Okay, so that in addition to all these extraction features, another great feature of the program is its ability to export your final results in what's called a PDF file generator. So naturally, one of the hard parts about doing finite element analysis is taking all of your final results and organizing in a clear, coherent report. So what you can do is you can use this function here, the export to 3D PDF function, and you can select whatever, say for example you have, maybe your displacements for these stages, as well as pile tip forces or something, or beam element forces. And then what you can do is you can click OK, and you can import all of these results in your PDF file. So it takes a couple of minutes to load everything and to set everything up. So what I'll do, just in the interest of time, is I'll just go back to our website here, and I'll show the quick video of sort of the main points of the PDF file generator. So we'll open it up here. So this is what essentially what your interface will look like. So as you can see, you can import your geometry, and you can make any sort of shifts that you need. All of your your table of contents, or all of your pages are sort of shown here graphically. You can move the view around very easily. You can create your cross sections as needed. You can make cuts along any axis, as you can see. So what this does is it allows you to take your finite element model and display it in a way that's very sort of clear and concise, and just sort of that matches your vision very easily. Okay, so if you have like a particular contour diagram that you want to show, you can zoom in as you need. You can assign the loading, or you can show the loading of your piles, etc. You can use the probe result option to draw directly on the pages, show your maximum and your minimum values. Okay, once again, you can manipulate your cross-section properties as such, and you can do so from page to page. So really, you can use this function to isolate or to extract exactly what you want into your report. So it's very useful if you're trying to sort of impress a client with a very professional-looking report. This allows you to create something that looks very aesthetically pleasing, but also very concise in the sort of information that you're sharing. Okay, and also that's another great feature. You can put these sort of tags on your drawing or on your drawing file to show the length or the units. You can add notes as you need, etc. So you can really sort of customize your report according to your exact needs. And that's just the comment point. So if you want to put any sort of comments, you can put them very easily just directly on your report. So that's just a brief overview of the report generation feature. So now let's wrap up now. And what I'll do is I'll pull up the last slide of my presentation. So once again, thank you for your time and attention. My name is Dale Saraspe. If you have any questions at all about today's presentation, or if you want to learn more about GTS NX, you can feel free to email me. Also, our website, MIDAS.gtsnx.com. If you want to download a free trial version of the program, you're more than welcome to do so. You can get into contact with myself or any of my colleagues for assistance, and we'll gladly help you get started with the program. If you want to maybe model one of your own projects on it, or you have like a sample project that you want to compare to previous results or previous calculations, we can definitely get you started with not only the download but also trying out the program. So once again, if you're more than welcome to approach us with questions or comments. We're more than happy to communicate with you regarding the program. So thank you once again for taking the time to attend today's session. We hope to see you soon. And once again, we definitely encourage you to look into GTS NX to see how it can help you, meet your project goals. Okay, until next time, take care.